Greetings everyone, my name is Mohan Prasad and my Matric number is U2004933. In this video, I'll be explaining on semiconductor devices known as photodetectors, and one such photodetector includes PIN photodiodes, which will be the focus of this video. A PIN photodiode consists of the same function as the photodetector and is used to convert optical energy such as light into electrical energy when it is in reverse bias condition. Let us start off with a brief introduction. The pin photodiode was invented by Jin Ichinichiziwa in the early 1950s. He was a Japanese engineer and an inventor who is known for his electronic inventions that contributed to the development of internet technology. The first applicable PIN photodiode was invented by inserting an intrinsic semiconductor denoted by I in between heavily doped P and N regions. This configuration was used to improve the sensitivity of photodiode by reducing capacitance and increasing the absorption of light. His other inventions also include avalanche photodiode, built in 1952, solid-state maser in 1955, a static induction transistor in 1950, and many more. The symbol of photodiode is similar to that of a normal diode with addition of two arrows indicating the illumination of light. A typical PIN photodiode consists of three regions, mainly P and N region, which are heavily doped with trivalent and pentavalent atoms respectively, which acts as ohmic conductors. And a third region, which is known as an undoped intrinsic layer, is sandwiched between the P and N region. The top face of the diode is protected by a silicon dioxide, which acts as an insulating material to prevent current leakage. The window, which allows light to pass through, is coated with a thin and anti-reflective layer called silicon nitride, which is used to maximize the absorption of light of the photodiode. As you can be seen here, the doped P regions contain holes as the majority charge carriers, which carry most of the current, whereas the doped N region contains majority free electrons, which carry most of the current. The intrinsic layer consists of high resistivity of 0.1 ohmic meter and is used to increase the width of the depletion region by increasing minority carrier current. Moving on to the working principle of PIN photodiodes. In zero bias condition, a majority charge carrier of the N region will diffuse into the intrinsic material due to higher concentration gradient. The depletion region across the Ni junction is created due to the diffusion of charge carriers between the junction of N and I region. As a result, a thin depletion layer is induced in the N region, whereas a thick depletion layer of opposite polarity is induced in the intrinsic region. PIN photodiodes can only work as photodetectors when two conditions are met. Firstly, the device has to be connected in reverse bias, where the negative terminal of the battery is connected to the P-type region, whereas the positive terminal of the battery is connected to the N-type region. Secondly, the energy of the incident photons has to be greater than or equal to the band gap energy. There are three main steps involved in the working of PIN photodiode. Firstly is the absorption of photons. As the magnitude of the reverse voltage increases, the depletion region between the P and N-type semiconductor will increase until the width of the depletion region covers the whole of the intrinsic region, where it is swept free of mobile charges. This allows for a larger area exposed to the incoming photons, thereby allowing for a larger amount of electron-hole pairs to be generated when struck by an incident photon. When a photon of sufficient energy thus strikes the depletion region within the intrinsic semiconductor, energy is absorbed by the electrons in the valence band are able to jump into the conduction band, thereby generating electron and hole pairs, which then form a barrier potential. The second step is the transportation of carriers. In the presence of the reverse voltage, an electric field is generated in this direction. Thus, the majority of charge carriers from the P and N regions are pulled away from the junction by this external field, causing the region near the junction to be depleted of charge carriers. As a result, the depletion region increases within the intrinsic material, and the minority charge carriers experience a repulsive force, which then diffuse into the depletion region, allowing for minimal electric current to flow. In addition to the reverse voltage, an electric field is generated within the intrinsic material moving to the left. This configuration results in drift component dominating over the diffusion component. After that, after the electron hole pairs are generated, they are swept away by this built-in electric field formed by the barrier potential within the depletion region. This causes the electrons to move to the N region and the holes to move into the P region, which are then attracted to the positive and negative terminals of the batteries respectively. This separation of charge carriers will then help to prevent recombination of electrons and holes. The last step is the generation of photocurrent. The separated charge carriers are then accumulated on the two metal contacts of the photodiode. The movement and constant exchange of electrons and hole pairs in the opposite direction between P and N region through the intrinsic material leads to the generation of photocurrent. The photocurrent generated can then be measured using an external circuit such as an oscilloscope, which displays the electrical signal generated by the photons. Therefore, the generation of electrical current in a PIN photodiode is contributed by the charge carriers in the depletion layer alone, due to the built-in potential barrier which causes the charge carriers to be accelerated in opposite directions. Thus, as the intensity of illuminating light on the depletion region increases, the number of charge carriers also increases, causing the magnitude of photocurrent to further increase. Here are some common characteristics of PIN photodiodes. Firstly, quantum efficiency is defined as a measure of how efficiently optical energy can be converted to electrical energy given by this equation. A higher quantum efficiency gives a greater conversion of light energy to electrical energy. Next, resistivity refers to resistance in a region. PIN photodiode has low resistivity in P and N region due to it being heavily doped, whereas in intrinsic region yields a higher resistivity due to it being undoped. Thirdly, dark current refers to a flow of current through a photodiode when there is absence of light. Fourth, noise equivalent power is the minimum input optical power to generate photocurrent, equal to the root mean square noise current in a 1 Hz bandwidth. Lastly, the responsivity is defined as the ratio of output photocurrent to incident optical power given by this equation and is measured in amps per watts. Pin photodiodes also has its advantages and limitations. Some advantages include low noise, in which pin photodiodes have an intrinsic layer which causes reduced capacitance, resulting in improved signal to noise ratio. Next, pin photodiodes exhibit low dark current, leading to an accurate detection of weak signals when the absence of light due to presence of anti-reflective film. Pin photodiode have a thick depletion region due to intrinsic material which produces low capacitance junction, which allows higher bandwidth detection, which in turn enables fast signal response. Lastly, the pin photodiode shows a higher value of breakdown voltage, as a greater voltage is needed in order to destroy a thick depletion region within the intrinsic material. The disadvantages are as follows. Slow response time due to delay in overall response caused by the slow diffusion process in photodiodes. Next is high temperature sensitivity, which causes the performance of pin photodiode to be affected by change in temperature. Thirdly, the pin photodiode does not have an internal gain, resulting in low signal to noise ratio, as there is no signal amplification within the photodiode. Lastly, pin photodiode are sensitive to optical feedback, where the incident light is coupled back into the photodiode, which causes fluctuations in the detected signal. PIN photodiodes are widely used and are utilized in several devices in our everyday lives. For an example, PIN photodiodes are widely used in medical equipment such as pulse oximeters, which is used to measure the concentration of oxygen in blood. PIN photodiodes are used to measure the different wavelengths of light in blood, which indicates oxygen level. The emitter emits light at 650 nanometers and 950 nanometers in the presence of deoxygenated and oxygenated blood respectively. Another application are remote controls, where PIN photodiodes are used to capture and decode infrared signals emitted by the remote control. Thirdly, PIN photodiodes are also used in phones that act as optical sensors, which use ambient light sensors in phones to adjust the brightness according to surrounding light conditions. Another daily life application includes smoke detectors, in which PIN photodiodes are used in conjunction with a light source to detect light scattered off smoke particles caused by the fire. The PIN photodiodes then generate a signal proportional to the incident light and triggers the sensor. And that is the end of the video. Thank you.